sklearngaussian process. Description: Gaussian processes (GPs) are a powerful non-parametric Bayesian method for regression and classification. They model the relationship between input features and output values by assuming that the outputs are drawn from a Gaussian distribution whose mean and covariance are determined by the input features and a learned kernel function. GPs are particularly useful for handling complex nonlinear relationships and providing uncertainty estimates in the form of confidence intervals. Inputs X. The input features. Typically a 2D array with each row representing a data point and each column representing a feature. Y. The target values. Typically a 1D array corresponding to the outputs for each input data point. Outputs. YPRED. The predicted output values for new input data points. YSTD. The standard deviation of the predicted output values, representing the uncertainty in the prediction. Steps. Kernel selection: choosing an appropriate kernel function that captures the underlying relationship between input features and output values. Popular choices include the radial basis function RBF kernel, the linear kernel, and the Matron kernel. Kernel hyperparameter optimization: finding the optimal values for the kernel hyperparameters, such as the length, scale, and variance, to best fit the training data. Prediction: using the trained Gaussian process model to predict the output values for new input data points, along with the corresponding uncertainty estimates. Metrics. Mean squared error (MSE) measures the average squared difference between the predicted values and the actual values. Root mean squared error (RMSE), the square root of the MSE, providing a more interpretable measure of prediction error. Log likelihood measures how well the model fits the training data. Visualization plots. Prediction plot visualizes the predicted output values against the actual values, highlighting the confidence intervals. Kernel function plot visualizes the chosen kernel function, showing how it captures the relationship between input features and output values. Fine-tune parameters. Kernel specifies the kernel function to use, e.g., RBF, linear, Matron, alpha regularization parameter that controls the smoothness of the predictions. N restarts optimize a number of random restarts for the optimization algorithm, helping to find the global optimum. Uncertainty methods. Confidence intervals provides a range of values around the predicted output, representing the uncertainty in the prediction. Predictive distribution defines the entire probability distribution of the predicted output, capturing the full uncertainty. Challenges and fixes. Challenge 1: overfitting to the training data, leading to poor generalization performance on unseen data. Sample use case: when the training data is noisy or has a high dimensionality, the model might overfit, resulting in high variance and poor predictions on new data. Fixes. Increase regularization alpha to penalize complex models. Use a more appropriate kernel function that avoids overfitting. Challenge 2: computational complexity for large datasets, making training and prediction time-consuming. Sample use case: when dealing with thousands or millions of data points, training a Gaussian process can be computationally expensive. Fixes. Use approximate inference methods like variational inference or sparse GPs to reduce the computational burden. Leverage parallel processing or GPU acceleration for faster training and prediction.